staying here for the second part of this evening. I'm going to talk about replicated data within Akka, how it's working, what a CRDT is. So hopefully at the end of the night you know something about CRDTs and how it's working within Akka. First of all, I'm a Scala guy, so when I show code, it's Scala code. Hopefully it's readable for everyone who knows Scala. Okay, so I see half the room with hands up, so hopefully the other part it will be clear what I'm doing, and if it's not, please ask, I will explain to you. I'm working for Trivento, which is a company based in the Netherlands in Amersfoort, and I'm currently employed at ING, where I'm working on an Akka system using distributed data from Akka. So first I will give some theoretical introduction to distributed data about CRDTs and how that's working before I dive into Akka and how it's really working with Akka. So if you don't use Akka or don't understand Scala, this will still be beneficial because the theoretical part will give some introduction to it. So first of all, nowadays we're see more and more distributed systems, right? And until recently, we tried to make it transparent to programmers. So to say the programmer, you have a programming model which we're programming on our local machine, just calling methods, which is a programming model we all know. And we want to make it transparent over the network, so that when you do a method call, it's not running on your local machine, but it's distributed to another machine and running on a different node. We wanted to make it transparent, but the problem is that with distributed systems you have a whole lot of problems, right? The network may fail, and certainly if you have a lot of systems, it will fail eventually. There is latency, and you have to deal with that, and you have to react to failure, right? So we have to make sure that we as a programmer know that we're working with distributed systems and that we know what we're doing, and not just taking it away from the programmer and making libraries that will make sure it will happen for you. So, and because of distributed systems, this stuff will happen, right? So there are two actors here, Alice and Bert, and they're talking to different nodes. And at one point, the yellow node does no longer have a connection to the other nodes. And what happens then? How do I stay? What kind of decisions can I make then? And that's where the CAP theorem comes in. How many people here know the CAP theorem? So I see some hands. The CAP theorem was some 12 years ago. They said, well, if you have a system, you can choose different traits, right? So you have either consistency, in which you say, if I write something to a node and I read something to a node, everybody sees the same data. The whole data in the cluster is consistent. On the other hand, you have availability. So anytime I want to contact a node, it has to respond to me. And now the tricky part is when you have distributed systems, you have a partition that will happen. And if you are partition tolerant, you can only choose between consistency or availability. You can't have both at the same time during a partition. Because if you want to be consistent and there is a partition like I shown in the previous slide, what do you want to do if you contact the yellow node? It cannot answer your question because it doesn't know what happens in the other part of the system. If some data has changed and you still answer, then you're not consistent. If you change data, you're not consistent. On the other hand, if you want to be available and you accept data, either writes or reads, and when you accept writes and you change data, then the system is no longer consistent again. So that's why you have to choose. And in the beginning, the thought was that when you create a system, you have to choose if you want to have a consistent system or an available system. But there was a paper a few years ago, which was CAP 12 years later, in which they said, well, CAP's all fine, it's there, right? We have this choice we have to make during partition, but it's not the case that our complete system has to be either available or consistent. You can, most of the time, your system is running just fine. You don't have partitions occurring every minute or so. So when your system's running fine, you can be consistent and be available. But you have to choose when there is a partition. So this, and you can not, you don't have to choose for your whole system. You can say, well, for this part of my system, I want to be available, and for this part, I want to be consistent. You can match that. And certainly in the current era where we all have a mobile phone in our pocket, where we can work on, it happens when you're in a train, the train goes into an area where there's no connectivity or in a tunnel or whatever. And when you imagine that this is Alice and Bob working on the same grocery list, they're putting groceries in their in the list, like in the Albert Heijn application, where you can put groceries and do it together. One moment, Alice drives into a tunnel. What do you want to happen? What do you want her to do? Does she need to stop adding stuff to her grocery list because she doesn't have a connection? Or should she continue? And probably you want her to continue working on a grocery list, adding stuff to it, removing stuff from it. And once she has a connection, this data needs to be synchronized. Because it might happen that Alice removes something from the list, Bob added something to the list, removes something to the list, and then they should have the same list in the end with the same groceries on it. So I mentioned consistency before. So if you have a cluster where you need strong consistency, you need some consensus when you write data to it. So you need that multiple nodes. It's usually a majority act when you're writing data to the store, such that when you retrieve data from the store, you can use a certain amount of nodes, and you're certain that you will get the latest version of the data. With these systems, you can tolerate at most n failures out of a system where there are two times as much systems plus one. So it means you can lose about half of the nodes minus one, right? If you go below that, then you don't have a majority, and there's no way to write anything to that system. Because if you would allow anything to write to the system, you don't know if you're a minority, whether you're a minority and every other node is really down, is not there anymore in a distributed system, or that there's network partitioning. Because there's no sense of knowing if a node is really down, or if it's still there but you can't reach it because of network. That's the real hard part in distributed systems. Not knowing what's really going on. You can only guess by seeing stuff happen. So what you see is that there are different algorithms, and maybe you've heard of some of those. Paxos and Raft are really used a lot in known software systems, right? Mesos is using Paxos, and AWS is using Paxos a lot for their concepts where they need some consistency. And Consul and HCD use Raft. And there are some really great papers on the internet, and there's a really good movie about Raft where they show you exactly how this is working. But it has a lot of orchestration to make it happen, right? So you need this real tight system where you have this consistency. On the other hand, you have an eventually consistent system, which is different. It's totally geared on availability. When you write something to one node, it doesn't mean that it's available on another node. That means that what I showed you before with the grocery example where Alice and Bob are working, you need a mechanism to merge the data back again in a deterministic way. So that when Alice merges the data from Bob and Bob merges the data from Alice, they get exactly the same list and always get the same list without any conflict. And in an eventually consistent system, you can tolerate to fill every node except one. Right? If one node is up, I can write to it, I can interact with it, and I can add multiple nodes, and then my cluster grows, and I can shrink it down back to one. So it's really, you can make it so that it's really, really highly available. But you have to keep in mind that at any time, there can be different data. And that's a real different thing to grasp because we are used to relational databases where we have ACID transactions where we write something to the database and we read it and everybody reads the same data. And eventually consistent systems are different in that aspect, and you have to take that into account and make sure that you really know what you're doing. So I mentioned merging data, and I guess that everybody here is familiar with something like Git, Subversion, where we place our code, check it out, and you see here that Alice is working on the master branch and someone else changed something on the master branch. And then you want to merge those two branches again and you get a conflict. Right, that happens a lot. They change the same line. So that makes perfect sense for version, right? Because you're, as a developer, want to know what happened, how should I merge this, that you don't just put one line below the other because what will happen, you want to test that. But for CRDTs, for distributed data, that cannot happen. When you need to have eventually consistency, it may not have any conflict because there's no one who can solve this conflict. So I mentioned CRDTs now, and a CRDT is a conflict-free replicated data type. And it's already in the name, right? It's conflict-free, which means that it's always mergeable. And there are essentially two types of CRDTs. One is an operation-based CRDT, and in operation-based CRDT, all operations are sent to the other nodes. So if I add an element to it, it sends an operation add element foo to this list. If I subtract element foo, it says subtract element foo. But it's important, the operations are commutative, but they are not idempotent in an operation-based CRDT. So you need a mechanism on the network layer where you're sure that your message is delivered and processed once at the other side. And there is some orchestration to make sure that every node gets this information. So there's a lot of orchestration in operation-based CRDTs. And the other one, which I'm going to talk more about this evening, is a state-based CRDT. And a state-based CRDT, the full state of the CRDT is propagated to the nodes. And there are some optimizations, and there's an optimization paper which Akka is trying to implement. I will talk about it later. Where you can send data instead of the complete data set. But the basis is that in a state-based CRDT, the complete data set is sent around. And that can be just sent to any node. And every node who's receiving this data must be able to merge the data they got from the other side. So again, in the example from Alice and Bob at the grocery store, Bob sends his complete list to Alice, and Alice knows exactly how she has to merge this data with her own grocery stores. And the same happens when she sends her list to Bob. Bob knows exactly how to merge these two, and they end up with exactly the same list. And I will give an example later to show you how that really happens. In the state-based CRDTs, you can operate with the CRDT with three operations. That's either a query to get data from it, and you can do it just from your local data. You can update your local data, right? So you send an update function to it, just mutate, add this, add apples to my grocery list, and then it will be added to your CRDT. And the other one is merge. This is the one where you receive the complete state from another node, and you have to merge that into your own data. Is this part clear for everyone, or are there any questions? Yes, please.
Yeah, it's clear. The difference between those two. So in case of state-based, you would send the whole state, so that's a lot more traffic. But for operation-based, you have a problem that it needs to be coordinated so that a node receives it once and only once.
Yes, exactly.
And from this picture, I get the feeling that more focus and research is going to state-based.
In Akka, which I'm going to talk about tonight, the state-based one is used. And I know a lot more about the state-based in that regard than in the operation-based. So, and I don't know exactly what kind of, if there are anyone using operation-based CRDTs to communicate their state.
So you're not aware of which one would be much more popular, or
sense of all implementations. No, I only know what Akka is using, and these are the two types there are. So to give an example, what I've used here is a grow-only counter. This is a data type where you can increment a counter, right? It can be used for counting the number of requests you got on your server. And the way it works, it's a data type where the data is an array of integers, and every node has its own place within this array. And when you want to know what the current count of requests is, for example, right? You can query the data type, and it will sum up all elements of the array and give you a response. So if there are two nodes counting, and one node says, well, I've got 6 requests, and the other one says I've got 12 requests, you can merge this as 18 requests, right? So to query it is the sum. When you want to increment your counter, you only increment your own counter. So you cannot increment anyone else's counter. And when you want to merge data, you can merge this easily without any conflict by taking the maximum of every part, right? So in the merge function, you loop over all elements in the array, and you take the max from your own array on position 0 and the other one on position 0. Then go to the next one, on position 1, to the next one. And if you max them out, then you know that you've merged them successfully. And the example below shows that, right? So we have 3 nodes here, and they're completely out of sync right now. The first one thinks there are 14 requests, B thinks there are 17 requests, and C thinks there are 16 requests. If we look at node A, and we look at the first one, right? So B sends its state to A, and it doesn't matter how the state is propagated, right? Or who sends the state to whom. In the end, it will merge deterministically. You can receive the same state over and over again, and merging has no effect. You can receive any one state, and in the end, they all merge forward, and you don't have any conflicts. So what you see at the top there, then it will take the maximum of 3 and 3, which is obviously 3, then the max of 5 and 7, which is 7, and then the maximum of 6 and 7, which is 7. If you do that for every node, and then in the end, you'll see in this example it will converge to an eventually persistent state where they all think the count is 19, and they all have exactly the same state. No matter how you draw the lines, it will go this way. Is it clear, this form? Because this was the theoretical part of CRDTs, what it essentially is, how it's working. Now we'll go into the implementations within Akka, and I will also give more details into another type and how it's implemented in Akka. So, what is Akka? Who knows Akka here? Okay, it's like half. Akka is a toolkit to build distributed systems. And it's built upon the actor model. And the actor model is something where every action you take is purely asynchronous. And the only way to interact with an actor is to send a message to it. So an actor has 2 things, it has state and behavior. So you can consider an actor like, I usually compare it to the humans around me. So everyone here is an actor. And the only way to interact with someone is by asking a question, which is like sending a message. There's no way I can go into the minds of people and take something out. The only way is just ask something and give it to me, please. Within the processing, when you write an actor, you receive messages, and when you have state, which you want to mutate, you can do that safely within an actor, because an actor is guaranteed to handle a message one by one in a single threaded-like manner. So there's no concurrency going on within an actor. But because you use a lot of actors, you have concurrency parallelism in your system. So just to make it visible, I've drawn 2 actors here, and they're going to interact with each other. and Alice wants to know what time it is. And the way she does this is by sending a message. And in Akka, sending a message is done by using a bang. So to actor B, send the message, get time. What happens is that the message is placed inside the mailbox of actor B. So actor B does nothing, just places it into the mailbox. And at this moment, actor A can just continue on doing his work. B is probably doing some work or happy to start handling your message. So at any point in time, there comes time that B is ready to pick up the message from the mailbox, picks it up, it processes this message in what I said before, a single-threaded isolation manner. So it can do all its work it has to do to be able to answer the question of time. And then, with every message which is sent to an actor, Akka knows who sent it to me. So you can ask for the sender, who asked me this question, and send back the time. And the way this works is exactly the same as asking the question. It's a message back to actor A. Actor A is probably doing something else, and the message is placed in the mailbox. So what Lauren also said, there's no blocking here, everything is just concurrently happening without any waiting. So the time is in the mailbox again, and any point in time, A becomes ready, takes the message, and then knows the time. Right? So this is really fast what Akka is, how actors are communicating with each other, to give you an idea what's going on. You don't have to completely understand what Akka is and how it's working, because I will tell you more with the next slides. And here's the code, and this is Scala code. And here you see that again, where the greeter sends a message greeting, and within the actor, this is a real simple actor which is doing just some logging, right? So you can match on the message which you got in. This is something which you get from Scala, where you can match on different data types and the data inside. And I can grab the who and put that in my log. So again, you don't have to fully understand it, but just to relate, the most important thing is that you just send something here with an exclamation mark, and the code continues. There's no way. So next is the topic of the distributed data, because what I told you before is just plain Akka, how the actor model is working. And what Lightband had done is they built distributed data on top of that. So they built something which is completely eventually consistent, which you can use to build your system where you don't have any consistency guarantees, and you don't want to use a different database, for instance, stuff like that. You just want to have your own Akka cluster in which you want to propagate data. So, as said before, Akka uses the state-based CRDT, in which they are gossiping the state. So, yes, it takes more bandwidth to send a complete data set, but you're not sending it to every node, you're just gossiping it around to a random node. And it seems like, well, how can gossiping work to a random node? So how will I make sure that every node will be eventually consistent? But it turns out that using a random gossiping is fairly efficient in the sense that you can say that they will all get this data in a very short amount of time, without any orchestration which you have to do it for yourself. You also have to take in mind that every node in the cluster has all the data. So if your data set is really, really big, you can't use Akka Distributed Data, because it will go out of memory. Okay, now a little bit deeper into the real implementation. I showed you something about the actor system, and the way you interact with the replicated data within Akka is through a replicator. And again, because it's an actor, it's completely asynchronous, and you send a message to it, and at one time you get a message back. And for people who are not familiar with that, it will look a little bit strange when I show you the code. Later on I will give a live demo, where you see some strange stuff because you have some context, you have to send it along, and it feels a little bit weird. But you have the benefit that it's completely asynchronous, there's no blocking going on, and yeah, that makes it really performant. And the way you get this replicator is through an Akka extension, also a feature of Akka, where there is this one replicator actor, and you can easily get it from the system at any point in your system, as long as you have an actor system around. And I'll show again, we'll show you that in the code later on. So I also said, well, we're using CRDTs. CRDTs are eventually consistent, but there's also something which you can do while writing to specify a sort of consistency level. When you write a message to an Akka cluster with distributed data, you tell the replicator, well, update this information, and then you can also specify where you want this to happen. It will always happen on your local machine. There, your data is immediately updated, but then you can say, well, I want to write it to n nodes, where you can specify the number of nodes you want to write to, or to a majority, or to all. And what will happen is that you write to your own data set, you mutate your data, and then it will push the data, the synchronization mechanism, so that all to the number of nodes, or to nodes, and then you have to get a confirmation back that it happened, so that you know for sure that it's already replicated to the other nodes. Does that make sense? But the thing is that this might feel like, okay, now I have a mechanism to create a consistent system on top of that, but when you do that, you're not certain that it's really consistent, because you say, okay, I want to write to a majority, and something goes wrong. Let's say, for sake of argument, I write to all nodes, but one node is down. And I don't know that it's done, just not reachable at this moment, because down is, as I said before, it's really difficult in a distributed system to know that a system really is down. You only know at one point it's not reachable. So I send it out to all nodes. I get a reply from all but one node. And at one point in time I have to say, well, I don't get information back, so I give a failure. So at that moment, as a user of distributed replicated data, I got a failure. It's a timeout failure. But I don't know what happened. Because my data already replicated to all nodes but one. And if I don't do anything, and the other one node comes up, it's replicated to the last node, and everybody knows you're up there. So it's not a matter of a transaction, right? So it's not like I want to write to all nodes, and if it didn't happen, just roll back. Because it's really hard to have a distributed transaction. The only thing you can do is, well, if you don't want that in that way, and you really want to make sure that it got to all nodes or roll back, then you can do a manual adding a different, right? I added apples, but something went wrong, and now I removed the apples. But again, you have no guarantees that this will be propagated again. So this is real important for you to have this consistency. Then don't use this system, because it's meant for different stuff. But it can help you in making a balance, right? To tell you, well, it's already propagated to some nodes, so I'm sure that I will keep this data. Is this clear for everybody?
So far, it's pretty much resembles Cassandra. How is it different? What's the difference?
I think Cassandra is also using this mechanism underneath, so that's not that much different. It's only when you build something on top of Cassandra, you have two components, and you can, with Akka, you can build your system just basically with your own cluster, right? And it makes sense for some situations where you don't want to write to Cassandra or don't want to manage Cassandra. So Akka has a whole lot of different data types, and I've shown the grow-only counter before. But there's also a PM counter, which stands for positive negative counter, where you just have a counter for the positives. So every node has two counters, one which is only incremented and one which is only always decremented, and you can add those two together to get the value, right? and there are different sets. A grow-only set, which is fairly easy. When you're always adding stuff to a set, it's always mergeable, right? If you can only add groceries, then Alice can add a lot of groceries, Bob can add a lot of groceries, and it's mergeable, and they always get the same set. The problem becomes when you want to remove something from a set, right? Because it's not that easy like with the positive-negative counter, because you want to remove something from a set and want to add it again. So there you have to have some mechanism to do that, and I will show you how that's implemented in Akka and how that's working. There are also different kind of maps. If you have a map, then you have a key with a value, and the value itself within the map needs to be a CRDT again, because the values need to be merged. The keys are there to match, the values need to be merged. It's also possible to create your own data type. So if none of this suits your fit, then you can write your own data type, and I've done that. It's fairly easy. I will show you next slide. One thing to remember, if you use any of these data types, you use a set and you put data in it, the data needs to be serializable, right? Because it's sent over the wire, so it needs to be serialized. But do not use Java serialization.
I'm getting back to the example you gave before, because what you're telling here is that the order in which events come in doesn't matter, right?
Actually,
So does your example here apply?
how do you mean? It's not really events.
The data here is actually a sum, and it doesn't apply, because it does matter in which order the events come in.
No, I don't quite understand, because it doesn't matter how these data sets, in what order they are merged, because the maximum of two numbers is always the same maximum. So if you merge them all together, you have all the sets, they all converge to the same data set.
Okay, but I can come up with a set that will disrupt this one.
Please do.
Take number B17, B where the sum is 17,
Yeah.
and change the order to 773.
2, 3, 7, 7, 3?
Well, 773, that one
Yeah.
will change.
Sure. If well, it can be the case that B writes something in the first node, because this, if you say, well, this is the counter of node A, this is the counter of node B, and this is the counter of node C. B cannot have a higher counter on the A node than A itself.
I'm sorry, I misunderstand, because I thought that this was a complete set. It didn't send over the lines.
Yeah, this complete set is sent over the line, but this is not a set. This is like a tuple, right? And every node has its own value. So A can only update the first value in this tuple. B can only update this one, and C can only update this one.
Okay, I'm sorry.
And that's why it can always converge to the same data. No problem, it's just
Okay. So your order matters, it should be reflexive as well, and it should be transitive as well. So all the algebraic rules apply. Is that true?
Yeah, the order in the tuple matters, but it's your data set, right? But it doesn't matter in which order they are propagated.
No, about the events. So AB same as BA. If A, B, so it's reflexive, it's transitive, it's
Really, really.
it's symmetric.
Yes.
Pay attention, you have.
Yes, the order of merging doesn't matter. If you merge one for the other, it's all the same. In the end, it will all converge to the same data type. And that's really important, that they are deterministically always converge to the same end state, no matter how you merge them. So as I've said, you can create your own data type, and the only thing you have to do is you have to write the merge and some operations to do on your data type. But merge is mandatory because you get the data sets the same type from the other hand, and then you have to do something to merge. And there you have to do the stuff we talked about before. One thing to be aware of is the memory usage, right? Because what you've seen in the grow only counter, there's in the array a position for your node. If the nodes would grow and grow and grow and shrink and shrink, shrink, and you never do any garbage collection, the array, the tuple is really great, but you only have 2 nodes, but it's still sending a real big tuple around. So maybe that may not be a problem, but something to be aware of. And with all the Akka data types, there is some pruning going on where when they know that a node goes down. So for instance, the example I showed before, when you know node A went down, you can do something to merge those data into another node and then drop the data.
You just said distributed system, you never know it's down. Okay.
Yeah, exactly. So in an Akka distributed system, what you do is then you don't use anything